Hello everyone, welcome back to another video. Today we are going to be discussing how the pressure and temperature of a pocket of air is going to change as you increase altitude. So obviously, as you're going to increase altitude, that air bubble is going to expand. So let's say you're starting off at sea level and you have a pocket of air that's about the size of your fist. You go up to the mountains, to the top of Mount Everest, that pocket of air might expand to, let's say, the size of a beach ball. Now, that's not exact. We're just using that so we can get a frame of reference. As you go up, the pocket of air is going to be expanding and increasing its volume. And along with that, the pressure within it is going to be decreasing as well as the temperature, right? The temperature and pressure of that pocket of gas are going to be decreasing. And obviously, that makes sense. If you go up to the mountains, it's a lot cooler than, if you're down at the beach by sea level. And obviously, endurance athletes like runners, anything that's involving cardio, they struggle a lot more at higher altitudes because the pressure is lower, meaning that there's a smaller density of oxygen within the air. So obviously, we can make sense that it's going to be decreasing the pressure and the temperature as you increase with altitude. But in today's video, we are going to be putting some mathematical equations so that we can understand what exactly is going on. Now, before we hop into the math, we are going to be setting some parameters for our situation today. The first being that this process is going to be adiabatic, which means that there's not going to be any heat transfer between the pocket of air that we're going to be looking at and the surrounding air. All right, so there's going to be no heat transfer. Obviously in the real world there would be a little bit of heat transfer, but air is not a good heat transfer, so it's going to be minuscule anyways, and we're just going to ignore it for now. And the final parameter that we're going to set for this scenario is that the pressure inside of our bubble of air is going to be equal to the pressure outside. All right, there's going to be no change in pressure between the two. It's going to be constant within the bubble of gas and outside of it. All right, so now we're going to go ahead and hop into the math of this all. And the first equation we are going to set up is going to be the change in pressure over the change in altitude. We're going to be using z to represent our altitude for our math today. And that is going to be equal to the change in density, the negative change in support. We got to keep our sign straight. This is going to be a negative multiplied by the force of gravity right here. And this makes sense. This is going to be negative right here because as you're increasing altitude, that pressure is going to decrease. So we need to make sure that this sign is negative, right? And over here, our density, we know, is going to be mass over volume. Mass over volume right here. Makes sense. That is the common definition of density right here. So we're going to go ahead and write that out. All right, and since we know that the gas bubble that we're looking at is going to be an ideal gas, we can go ahead and do some substitutions for our V down here. Using the ideal gas law, we know that PV is equal to nRT. So obviously we can go ahead and divide both sides by P and get V equals nRT over P. And then we would go ahead and flip that around since this V is going to be on the denominator right here. And that would get us P over nRT. And this mass over moles over here, that is pretty much just our average molecular weight right there. So we can go ahead and use a symbol to get these two out. And we'll go ahead and use this symbol right here to represent our mass per moles right there. Equals RT. And yeah, now that we have this expression for our density, we go ahead and substitute that in right there. So we'll go ahead and erase this. Get our new expression going over here. So this would be pressure mu gravity over RT. You got to remember to include our negative sign over here. Alright, so now that we have gotten this expression over here, the next thing we're going to want to do is we are going to want to find an expression for t right here so that we can get only p's on this side of the equation, the rest of it being constants that we're not going to have to worry about when we integrate. And the reason we're going to want to do this is because right now we have a change in pressure related to the change in altitude. And if we try to integrate this right now with the temperature, which is not a constant, it would get real messy and we wouldn't be able to do it. So we are going to be coming up with some more equations to find an expression for t as it relates to the pressure. And then we're going to go ahead and substitute that in for t so that we can get only p's and then integrate both sides. So that's what we're going to go ahead and do now. And the way that we are going to relate the two is using the first law of thermodynamics, which says that the change in internal energy is going to be equal to the change in the heat added. Blanking on what the symbol for heat added is. I believe it's Q. And this is going to be subtracted by the external pressure multiplied by the change in volume right here. That is going to be the expression that we're going to be using. And right here, we can think of this in a different way. We can go ahead and think of this left side of the equation as the change in internal energy over the change in temperature at a constant volume multiplied by the change in temperature. And pretty much what this is right here is the specific heat capacity of the substance, right? So this is what's going to be our left side of the equation. The more simple way to write this is going to be Cu dt. This is going to be what we use. All right, and then our right side of the equation right here, this can be canceled out because the change in temperature is going to be 0 for us because there is going to be no heat transfer, because earlier we said that this process was going to be adiabatic, which means there's going to be no heat transfer going on anywhere. So this can go ahead and cancel out. And then over here, this external pressure, earlier we said that the pressure inside of our air bubble is going to be equal to the pressure outside of the air bubble. So we don't have to worry about this external part. We can just make this negative P right here. So our specific heat capacity is going to be equal to negative P dV. There you have it right there. All right, so now that we've got this expression right here, the next thing we're going to do is we're going to go ahead and bring our ideal gas law back into this to substitute our P expression over here. So we're going to go ahead and say that P is equal to RT over V. We'll go ahead and substitute that in for our P over here. And then we'll go ahead and multiply both sides by 1 over t so that we can get our t over here on the side of the dt. Alright, here we go. This is looking pretty good. We got our volumes on the side of our change in volume and temperature over here on the side of our change in temperature. And the next thing we're going to want to do is we are going to want to set up our integral. So our heat capacity right here and our ideal gas constant, those are both going to be constants, so we don't have to worry about those when we integrate. So we can go ahead and bring those out. There you have it. That is going to be our integral setup. We'll go ahead and erase the rest of this up here so we can give ourselves some room. Alright, now the next thing we're going to want to do is we're going to want to set up our parameters for the integral. So we'll go ahead and rewrite this up here. Alright, so the lower parameter for our temperature integral is just going to be our constant T1. This is going to be the initial temperature that we start off back when we're on ground level, when our air bubble is the size of our fist. If you can remember, like we set up in the example earlier in the video, that is going to be given to you. And the upper parameter is going to be T. This is going to be whatever, this is going to be dependent based on however high the altitude change you set up is. And over here in our volume parameters, it's going to be the opposite, right? The V1 that we start off with that is given is going to be up here at the top, and the V that changes based on how much altitude you change is going to be at the bottom because we have this negative right here, and the negative flips the parameters. So we can go ahead and get rid of our negative sign right there. All right, and now we're going to go ahead and integrate this out. So the integral of 1 over t is pretty much just going to be the natural log over here of t over t1. And it's going to be the same thing over here. It's going to be the natural log of v1 over v. So we'll go ahead and get our integrals out. There you go. All right, there you have it. And all right, so our next step is going to be to multiply both sides by 1 over r over here. So we are going to go ahead and do cu over r. And we'll go ahead and erase this over here since the r's would cancel. All right, and the next thing we're going to want to do is we're going to want to get rid of these natural logs. And when we do that, this is going to put cu over r as an exponent of this t over t1 expression that we have right here. And this is just going to become v1 over v. So this is going to become there you go. And the next thing we can say, we can bring our ideal gas law back into this and to substitute our v's over here. And to do that, we are going to get, these are going to be equal to RT over P. So this is going to be equal to RT over P, and then another RT over P, like so. And it's important to realize that these temperatures are going to be different. This is going to be the temperature at our initial start when we are at a low altitude. So these are not going to be the same temperatures right here. This is going to be a temperature at the end, and this is going to be a temperature at the start. So those are not going to be able to cancel, right? And then these R's are an ideal gas constant, so those will be able to cancel. So we can go ahead and X out our R's right there. Our pressures are also going to be different. This is going to be our pressure at our initial position as well, because it's the volume at the initial, so those pressures are not going to be able to cancel. And since we have a fraction within a fraction, we can go ahead and do some flipping around here to get this to look how it is supposed to be looking. So we'll get T1 over P is going to be equal to P1 over T, like so. So we can go ahead and erase this right here and just bring this over here so it's looking cleaner. Alright, the next thing we're going to want to do is we're going to want to multiply both sides by t1 over t, and that is going to cause, t over t1. We're going to want to multiply both sides by t over t1, and what that is going to do is going to cause the t's to cancel and the t1s to cancel, so those will go away. So we'll go ahead and get some big old parentheses, t over t1. Do some erasing up here. And multiplying this side by t over t1 is going to cause this to become a plus 1, which makes sense, right? Because if you did t over t1 times t over t1, that would become t over t1 squared. So multiplying an expression by itself is just going to raise exponent to the plus 1. So this is going to become c over r plus 1. So we'll go t over t1 to the cu over r plus 1. That is going to be equal to p over p1. There you go. Alright, so our next step is going to be trying to find a way to simplify this exponent right here. Right now it's a little bit complicated and be a little bit tricky trying to get this into a term that kind of makes sense and is easy to look at. So we're going to try and simplify this right here. And the way that we are going to be doing that is we are going to be saying that the specific heat capacity at a given pressure is going to be equal to the specific heat capacity at a given volume plus our ideal gas law. And the reason that we can say this is because this is an ideal gas, which means that the change in enthalpy is going to be equal to the change in the internal energy right here, plus the ideal gas constant multiplied by the change in temperature. And down here, this change in enthalpy, which I think should be a big H right here, capitalized H, we know that this is going to be the specific heat capacity at pressure multiplied by the change in temperature, and this over here, our change in the internal energy, is going to be the change in the specific heat capacity at a volume multiplied by the change in temperature, and this is going to remain the same. This is going to be r dt, and right here we can see we have dt's everywhere, so we can go ahead and cancel all those out, and that is how we get our Cp equals Cv plus R right there. And we get this because we know it's an ideal gas law, so we know that the enthalpy is only going to be changing based on temperature. That's how we go from here to there right there. So yeah, this is how we get our Cp equals Cv plus R right here. Alright, so we did make a mistake earlier. This Cu is supposed to be a Cv. Not sure exactly why I used the U there. This is supposed to be the specific heat capacity at a given volume. So there we go. And now what we can go ahead and do is multiply everything right here by 1 over R. And what that would give us is Cp over R equals Cv over R plus 1. And what do you know? That is exactly our exponent right here. So we can go ahead and substitute this Cp over R right here in for our exponent up there. So this is going to become the specific heat capacity at a pressure over R. And what we can do right here is raise both of these sides to R over Cp, which is going to cancel out this expression, and raise this. This is going to become P over P1 to the R over Cp. So this is going to become T1 equals P1 to the R over CP. And then we can multiply T1 to the other side, and this is going to give us our expression for the temperature as it relates to the pressure. There you go. Now we can go ahead and start working back up here onto this equation. This expression right here is going to go right here in for temperature. So we'll go ahead and start writing this up. dP over dz is going to be equal to, there we go, P mu g over R. And this T1 is going to stay down here. And what we can do now is we're going to try and get our pressures up here into the numerator up here. And the way that we can do that is since this P1 is going to be in the denominator, normally if it was going to stay in the denominator, the exponent would be flipped. But if we want to take it to the numerator, since it's going to be a denominator within the denominator, we can go ahead and keep those exponents where they're at. So this is going to be P1 to the R over CP. Alright, and then since we have this pressure right here, which is going to be a numerator in the denominator, what we can do to get that in the numerator up there is that we can go ahead and make that a negative R over CP right there. So we'll go ahead and do that. P to the negative R over CP. And since we have this pressure right here, we can go ahead and make this a 1 minus R over CP, right? Since pressure times a pressure is pretty much just going to raise the exponent to the plus 1. So we can go ahead and do that. We'll go ahead and erase that one right there. And we'll go ahead and make this 1 minus R over CP. 1 minus R over CP. Like so. Go ahead and erase this down here. Alright, so the next thing we're going to want to do is we are going to want to get our pressure over here onto this other side and our dz over here on the other side. So we'll go ahead and just multiply both sides by dz. And an easy way to get this pressure over here is to divide it. And when we do that, the signs on our exponent over here are going to flip. So this is going to become RCP minus 1. So we'll go ahead and write that. This is going to be P to the RCP minus 1 dP. Alright, and that is going to be equal to, again, over here, our mu g P1 to the RCP all over RT1. And this is going to have dz over here now since we multiplied. And there you go. Now we're going to be ready to set up our integral over here. This is going to be not too difficult because over here this is all constant stuff. This is not going to be changing. So this is all going to come out of our integral and we're not going to have to worry about doing any sort of crazy math with that. So we're just going to go ahead and multiply this right here and this right here. That is going to be what we are going to be integrating. So we'll go ahead and set that up. And our parameters over here are going to be our initial P1 over our P up here. And that is going to be P R C P minus 1. Important to realize that this P and the P of our parameter are not going to be the same thing. This is just a variable that we're using to set up our parameter. And this is going to be all the same thing. You know, we'll just go ahead and write this up here so we don't have to rewrite that big old expression right there. So this is going to be P1P, and then over here this is going to be Z1Z, our initial altitude, and the altitude we finish at, like so. Alright, so we did make a little bit of a mistake earlier. We lost our negative sign somewhere along the way. So remember to include your negative sign, right? We want the pressure and the temperature to be decreasing as we increase altitude. If it's increasing, we did something wrong, and obviously we forgot our negative sign right there. Alright, and so to do this integral right here, we'll go ahead and do the exponent part of it first. So we are going to be adding 1 to the exponent and dividing the expression by it. So the plus 1 is going to cancel out with this minus 1, and this r over cp is going to flip and become cp over r. So we're going to go cp r. There you go. And then pretty much what this is just going to become is this is going to become P r to the CP still. This should be a P right here. This is going to be our P at the higher altitude minus P1 r to the CP, like so. And that is going to be our integral right there. As you can see, we would be able to go ahead and multiply our r over. That would cancel out with this r. And then we would divide our CP over to the other side like so. We also forgot to do our integral for z earlier. If you remember, we had the parameters z1 to z integrating just dz. And what that integral would just be z minus z1, right? The altitude at our higher position minus the initial altitude we had at the lower position. So that's what that integral would become. So right here, we're going to go ahead and divide the CP over and add our P1 CP over here to just get their PCP, P to the RCP, excuse me, on one side. So it's going to become P to the RCP, and it's going to be equal to P1 R to the CP. Probably shouldn't have erased that. Having trouble trying to remember what our earlier expression was. I'll come back and write what we had over here later, and we'll just cut to that. Alright, so this is going to be the expression that we have over here. As you can remember, we divided our specific heat capacity at the given pressure by both sides, so we get Cp in the denominator over here, and we had our integral for dz over here, which came out to be just z minus z1. The next thing we're going to want to do is we're going to want to factor out this P1 to the RCP over here. So this is going to be PR over CP. That's going to be equal to P1 R to the CP, R over CP. And then this right here is just going to become a 1 minus mu G CPT1 multiplied by z minus z1. And what we can go ahead and do now is we can raise everything to the CP over r power, so we can get these exponents to cancel out, right? So if we go CP to the r, the CP's are going to cancel and the r's are going to cancel. So these exponents are going to go away. And then we're going to raise this term over here to the CP over r. And there you have it. That is going to be our expression for pressure. We'll go ahead and write that out down here. P1, 1 minus mu G CPT1. There you go. That is going to be our expression for the pressure as it changes with altitude. Now the next thing we are going to need to do is we are going to need to find the temperature equation. And that's going to be pretty simple. We're just going to be able to plug our expression right here into the equation that we had relating the temperature and pressure. And we'll just do some basic math and we'll get our temperature equation. Alright, so earlier in the video, if you remember, we came up with this equation to relate the pressure with the temperature that we then used to substitute in for our temperature over here. So we could get our integral for the pressure going. And basically what we can do now is we can substitute this expression in for the pressure right here. And by doing that, we're going to have a lot of nice things happen for us. As you can see, this would go right here, and we would have P1s in the numerator and the denominator, and those would cancel out with each other. And then we have this R to the CP over here. That would cancel out this CP over R, so the exponents would cancel out too. So we'll go ahead and write this expression out just so that we can visualize it a little better. But this is going to end up really nice for us. So this is going to be P1, 1 minus mu G, CP T1, Z minus Z1, to the CP over R, all over P1, as you can see here, these P1s are going to go away, so we're no longer going to have to worry about that. And then within these brackets right here, it's to the CP over R, but then outside of the brackets, it's to the R over CP. So these exponents are going to cancel, and this is going to be a real simple expression right here. The temperature is going to equal our temperature at our initial altitude, and then it's going to be 1 minus mu G over the specific heat at the pressure times the initial temperature, Z minus Z1. And there you have it. That is going to be our temperature expression right there. And these are going to be our two equations. This is going to be our temperature as it changes with the altitude, and this is going to be our pressure as it changes with the altitude. So there you have it. That is going to be it for today's video. If you guys have any more questions, make sure to post it down in the comment section below. If you liked the video, make sure to like. If you want to see more content, press that subscribe button. And yeah, have a good one. Hope you guys enjoyed.